Question 9 from the 2019 Advanced Higher Physics Examination from the SQA. An excerpt from a student's notes on fusion reactions is quoted below. Electrostatic repulsion must be overcome before fusion can occur. Two protons repel one another because of the electrostatic force between them. If two protons can be brought close enough together, however, the electrostatic repulsion can be overcome by the quantum effect in which protons can tunnel through electrostatic forces. The Heisenberg uncertainty principle suggests that the protons can borrow energy in order to overcome the electrostatic repulsion. This allows fusion to occur at lower temperatures than would otherwise be required. And for 3 marks, you're asked to show off your physics, to use your knowledge to comment on the above excerpt. Well, you can go through it step by step. You know fine well that fusion is the coming together of two nuclei, and they must come together at such a speed to overcome the electrostatic repulsion. If the proton has not got enough kinetic energy, then it will not overcome the electrostatic repulsion and it will be repelled away. And you can think of this situation in terms of the classical case, where you can consider the protons being like two balls and they encounter a hill. So there we have the first proton up, the second proton up here, and the other proton down here. And the hill here represents the electrostatic force of repulsion, which we think of as a potential hill, a barrier. Think of it in terms like that at the moment. So if this proton here has got enough kinetic energy to overcome the gravitational potential hill, it will fuse. But remember, to do that it must have a certain speed, and therefore it must have a certain temperature. But at low temperatures, which means low speeds, then the proton will not have enough kinetic energy to overcome the potential hill, and therefore it will never get near the other proton. Now that's us viewing that from a classical point of view. But remember, in a quantum point of view, particles behave like waves. And this is the key point, which you can go into and discuss the third paragraph there. So rather than drawing out a hill like a sort of landscape, we can draw a energy diagram like this, shown here. Now rather than representing the proton as a particle, we now represent it as a wave in quantum theory. And remember the sort of interpretation of that wave, its amplitude squared is related to the probability of finding the particle at a certain position. Now we can draw in our barrier, and here's our barrier there. And as you can see, the particle or the wave, if it's not got enough kinetic energy to rise above this barrier, then it will not get to the other side in this position here. So classically, that's not allowed. But in the world of waves, then a wave must be continuous. It's a bit like throwing a ball against a wall. We know the ball, in fact, reflects off the wall, but if we looked at it very closely, we'd see that the ball, in fact, squashes as it touches the wall. Well, for waves must be a continuous quantity. They're a real quantity. So if when they reach the wall, it just doesn't stop there. The waves, in fact, should take a pattern like that. And that pattern there is almost like a sort of exponential wave all going down here. What does it tell us? It tells us that the amplitude here tells us that if we square the amplitude of the wave here, it's got a probability that wave, that particle, will be inside this potential barrier. Now this potential barrier is quite wide in terms of distance, but if we make things a lot smaller, or make the potential barrier smaller, we get this diagram here, which is very important. Because look what's happening now. The wave of the proton, as it reaches the potential barrier, it has to be a continuous entity, and therefore as it reaches the barrier it will fade off quite quickly here and leave this little ripple in here, and that's behind the barrier. Now what does that tell us in terms of quantum theory? It tells us you have a probability of finding that wave behind that barrier, or otherwise you have a probability of finding that particle behind that potential barrier. How? Because remember our definition of the wave function for a particle. It's the amplitude squared is related to the probability of finding the particle at that position. So here we have a situation where where classically the particle can't exceed the barrier if it's not got enough kinetic energy, it actually tunnels through the barrier and appears on the other side. And if we square these amplitudes, we have a real finite chance of finding that particle there. And this does happen in the centre of the Sun, the core of the Sun, because the temperature at the core of the Sun is not high enough to ram these protons together to fuse together. So some other mechanism must be taking place, and it's quantum tunnelling. Now I know the probability of finding the particle at the other side is very small, but in the case of the Sun, when you've got really billions upon billions upon billions of particles, then that probability multiplied by those billions and billions of particles becomes a real event. And that's why the Sun shines, even though the temperature at the core is not high enough to sustain nuclear fusion. So we could go to town on that one there then, and talk not so much about the electrostatic force, but the potential barrier caused by it. The wave represents the particle. At the interface between the wave and the potential barrier, a strange effect takes place where the wave in fact tunnels in or leaks into the barrier and appears ripples at the other side, which gives us a finite probability that the particle has got through that barrier, even though classically it doesn't. So that's quantum tunnelling. In the last part of the argument, the student is going to use Heisenberg's uncertainty principle to explain how the proton can in fact get over the potential barrier. I don't think you can use it to explain quantum tunnelling. That's a different thing. You could use it from a different perspective and say that the student really is meaning from the point of view of the particle overcoming the barrier rather than tunnelling through it. So let's look at the student's argument in terms of the Heisenberg's uncertainty principle. And to do that, we need to look at some energy diagrams. So here's our first energy diagram here. And that's the case where the proton has got quite enough energy, but just short of the top of the potential barrier by delta E, and delta E is small. And we can put Heisenberg's uncertainty equation there, as we'll talk about in a minute. Now if you look very closely, you can see that because delta E is going to be small, therefore in order to maintain the above equation, delta E times delta T is greater than or equal to h over 4 pi, then if delta E is small, then delta T will have to go large. It's like a seesaw effect, that above in equation. So delta T must be large because delta E is very small. Now if that's the case, then the proton can borrow that extra amount of energy, can use that extra amount of energy only for a given time. But in this case the time will be large, and hopefully the time will be long enough that the proton will have its energy to come near the potential barrier and escape over it. So you could use that argument. Now the other argument is this situation here, and we'll have our Heisenberg's uncertainty inequation up there. And you can see in this case the proton has not got a lot of kinetic energy, not a lot of energy as it approaches the potential barrier. Its shortfall is quite large. So because delta E is quite large, then delta T is going to be the exact opposite from the last one. The time it takes to borrow this energy will in fact be very small. Now let's think about that for a minute. Because the proton has got a large shortfall of energy needed to go over the potential barrier, if it borrows that amount of energy, it only can really borrow it for a very small time to maintain Heisenberg's uncertainty principle, which is a fundamental part of the universe. So delta T will be small, and that might not be enough time for the proton to use its speed to approach the potential barrier, and therefore it might not happen. Now it's not the best way of, as I said before, of explaining quantum tunnelling, because what we're looking at here is the energy of the particle in terms of the borrowing, if I can put that in inverted commas, of energy, and the time which is used in that borrowing time. So in the first diagram we can write down a few sentences saying that because the proton has got enough energy but just slightly less energy than the potential barrier's height, delta E is very small. Therefore delta T will be large. Therefore there's a great possibility that of course the proton will have enough time to overcome the barrier with its given speed. But if we look at the second scenario, according to the student's argument, the proton lacks the energy needed to get over the barrier by quite an amount. And if it wants to borrow that amount, according to Heisenberg's uncertainty principle, then it only can do that for a very small amount of time. And that very small amount of time, delta t, might not be long enough for that particle to get near the potential barrier, and therefore the fusion will not take place.